In Montgomery County, the crimes that affect people every day usually are not homicides. They are burglaries, car break-ins, thefts, gun possession cases, and vehicle thefts. These are high-volume crimes. They happen constantly, they impact quality of life, and they shape how a safe community feels. The challenge is that these crimes have historically been difficult to solve, not because they are unimportant, but because for a long time we did not have the right tools early enough in the investigation. In many of these cases, DNA was either never part of the conversation, or when it was collected, it failed to generate a match or meaningful investigative lead. Once that happened, the investigation often stalled. That is why solving volume crime matters. These offenses touch every community, and if we can test evidence in a more timely and effective way, we have real opportunity to help investigators move cases forward and better protect the public. DNA can play an important role here. When we recover DNA from high-volume, low-level crime scenes, it can link suspects to evidence, connect related cases, and sometimes identify patterns that were previously invisible. One of the first advances for us was the use of Bode hits. Bode hits gave us a way to use DNA in high-volume, low-level offenses with greater speed and cost efficiency. It also allowed DNA profiles to be shared regionally across jurisdictions, which was a major step forward. For Montgomery County, participation in Bode hits helped identify and solve many low-level crimes that crossed municipal boundaries. That alone was valuable. Rapid DNA also added another important capability. It allowed us to process and upload certain reference samples and single-source samples in about 90 minutes. From an investigative standpoint, that meant we could begin answering some questions in near real time. Combined with the Bode hits database, Rapid DNA helped us search single-source profiles much faster. But both of these systems came with a trade-off. Speed and efficiency mattered, and the system did what they were designed to do. However, many of these high-volume crime scene samples produced complex DNA mixtures. Those mixtures were frequently classified as non-searchable. So while we're moving faster, we were still losing a great deal of potentially valuable information. At that point, the question changed. Instead of simply asking whether DNA could be searched or whether there was a database hit, we began asking more important questions. Are we leaving useful information behind in the so-called non-searchable mixtures? That realization led us to cybergenetics. We contact cybergenetics because we recognized that we had been thinking too narrowly. We were treating DNA results as either searchable or non-searchable, hit or no hit. But if there was much more information inside that data, and that information could be used not just in a single case, but on a continuing basis across a high volume of cases. Our hope was to address these high-volume, low-level crime scene profiles in a more meaningful way. We had seen cybergenetics work in individual cases before, but now the question was whether it could be scaled into something long-term and operational. To be honest, at the beginning, we were not completely sure what a TrueAllele Investigative Database could do in this setting. We believe there were more information hidden in previously tested items, but we did not yet know whether that information could be developed consistently on a monthly basis. So the project began with a proof of concept. We took 2 years of DNA data files from our high-volume agencies and entered the information into the newly established TrueAllele Investigative Database, or TAID. As the work progressed, new associations began to emerge. We started to see relationships, patterns, and criminal movement in a way we have not seen before. For the first time, DNA was no longer just a piece of evidence tied to a single event. It began to function as intelligence, and that was the turning point. What we found was significant. A large portion of what had previously been considered non-searchable mixtures began generating new associations. Those associations created connections between property crime, vehicle theft, firearm incidents, and other offenses that had previously seemed unrelated. That changed the way we looked at DNA. Instead of examining one case at a time, we began looking across all cases. DNA stopped being just a snapshot from one crime scene and became part of a broader timeline. Patterns became visible. Repeated associations began to reveal criminal trajectories rather than isolated incidents. In other words, we were no longer just asking whether there was a match. We were asking what the overall pattern was telling us.
At the heart of our approach is the TrueAllele technology. What does TrueAllele do? Fundamentally, TrueAllele separates the DNA data into the genotypes of each contributor that is in a mixture. TrueAllele uses all the data, it uses no thresholds, and has been validated up to 10 unknown contributors. There are about 10 validation studies that have been published in peer-reviewed journals. TrueAllele represents uncertainty in genotypes by using probability. That's the only known method in science for representing uncertainty. TrueAllele is accurate and preserves the identification information contained in the data. We know this because there have been over 40 validation studies done by various groups on TrueAllele. TrueAllele is unbiased. It was designed to not be able to use or know a suspect profile when it's solving a problem and separating out the genotypes. TrueAllele reports information when it compares a genotype from evidence with a person as a likelihood ratio match statistic. What a likelihood ratio does is it describes mathematically the change in genotype probability. A number like a million or a billion is a large change, and you can have smaller changes like a tenfold or 100-fold. TrueAllele also provides error rates, which are essential for being able to report all DNA evidence. TrueAllele's automated computer workflow frees people to do things that are not mathematical calculations, but are what people do best as forensic scientists. TrueAllele does not require any laboratory calibration because its mathematical Bayesian method learns these parameters directly from evidence data. Cybergenetics continues to add new capabilities to the TrueAllele technology. Here we show part of a validation study on a new feature for determining the number of contributors in a DNA mixture. From the outset, TrueAllele has been built around a relational database. This genotype matching database uploads all genotypes, that is, every separated contributor from any evidence. And it automatically matches these genotypes. It compares them on the server. When there is a connection of these separated genotypes, whether it's evidence to evidence or evidence to reference, TrueAllele measures the strength of that connection with a likelihood ratio, and it records the positive DNA matches connecting genotypes. The new technology idea is to combine the power of TrueAllele genotyping and matching with context information from a LIMS system about the evidence items. This produces the new TrueAllele Investigative Database, or TrueAllele ID. As before, TrueAllele can upload all the contributor genotypes to its database, preserve the DNA match information through automated genotype matching, and record all the strong likelihood ratio connections. What's new is now these genotypes and their items are annotated with LIMS information that tells us for evidence items how it was collected and what case it's connected to and other information. And for reference items tells us who the reference item actually is. The result is that we can automate the presentation of information to investigators. This combination reduces human effort tenfold in being able to provide the information from cybergenetics to investigators, and cybergenetics is able to pass this cost savings onto investigators, much like batch processing for investigative laboratories. The result is affordable information processing from high-volume, low-level crime. When cybergenetics began looking at 2 years of Montgomery County's data, we found a tremendous amount of DNA match information. Most of this was previously unsearchable mixtures, which TrueAllele converted into useful matches. Here is one set of crimes of car theft. What this picture is showing is evidence-to-evidence matches chronologically across the 7 cases in the columns. And this is what the matches look like. On the top in blue, case B is the index case. On the bottom in red, we see 6 comparison cases. These are all different types of car thefts. The center 2 rows describes the evidence-to-evidence matches that the TrueAllele Investigative Database found here. In black, we see the likelihood ratio ranges. These are in logarithmic units. So 4 means 10,000. 10, or 10 to the 10th, is 10 billion. So we're seeing pretty strong match strength connections between the index case B and the 6 other cases A, C, D, E, F, and G. The row underneath in red shows the number of matches between case B and each of those separate 6 cases. Index case B matched 9 evidence items from case A, 7 from case B, 4 from case D, 9 from case E, 6 from case F, and 4 from case G. In total, TrueAllele found 39 evidence-to-evidence matches between case B and these 6 other cases. Underneath each case label and the collection date, we list the types of evidence items like door handle, gear shifter, steering wheel, ski mask, tire iron, and the numbers in each entry are giving how many matches TrueAllele found between case B and these other 6 cases. This table shows what happens when a reference suspect enters the database. The top rows in purple show that in January of 2023, an 18-year-old male was entered as a reference profile, and there were 18 matches to these 7 crime scenes, with match statistics ranging from a billion to a trillion. The middle rows show that there were 2 or 3 matches between the reference and evidence items in the 7 crime scenes, along with the ranges of match strength. And the bottom rows give a breakdown of how many matches there were to each type of evidence item. These results from Montgomery County show how the TrueAllele Investigative Database can turn non-searchable mixtures into powerful DNA evidence that connects suspects with many crime scenes. Cybergenetics puts the power of TrueAllele into the hands of the investigator. This is a screenshot from software that Montgomery investigators use to look at the strengths of match between different items of evidence. They can explore what those matches are, how strong they are, and build a match table that compares different evidence items with other evidence or reference items. Law enforcement can use these case-annotated DNA match results to aid their investigations. We studied the Montgomery results over a 2-year period to see how TrueAllele could convert non-searchable mixtures into useful DNA match information. We get about 100 DNA items per month from Montgomery as data. 60% of it is evidence, about 40% is reference, and we were able to quantify that 60% were unsearchable mixtures with unused genotypes that were unable to find DNA leads. We quantified the TrueAllele ID's information improvement. We found that on a per-item basis, there was over one evidence match per item on average. 98% of the DNA evidence was informative to TrueAllele. Most importantly, 72% of the unsearchable mixtures matched another item. This 72% match rate of the 60% unsearchable mixtures more than doubles the usable DNA evidence. That is, starting from 40% searchable mixtures, TrueAllele ends up with over 80% searchable mixtures. This helps investigators find useful DNA leads.
One case in particular that helped bring everything into focus was the HB case. In this case, DNA associations revealed a pattern of escalating behavior by HB. What initially appeared to be lower-level crimes, including car break-ins, began to connecting to vehicle thefts, then to a stolen firearm left inside a vehicle, and eventually more serious involving carjacking with a father and his 2 children. What made this case important was not just the associations existed. It was that operationally those connections had been visible before. The DNA had appeared across cases, but because those results were previously deemed non-searchable mixtures, that pattern was never clearly recognized. Once those samples were entered into the TrueAllele Investigative Database, that pattern emerged. What surprised us was how clearly the escalation could be seen when the cases were finally connected. Looking back, the trajectory was obvious. Looking forward, the harm may have been preventable. That is where the real value of this work becomes clear. This is why volume crime matters so much. The most serious offenders often do not begin with the most serious crimes. Many start with lower-level offenses. If we prioritize DNA recovery and advanced analysis in those high-volume crime categories, we can put ourselves in a much better position to identify patterns earlier and intervene sooner. This is the larger vision. We came to realize that non-searchable does not mean non-usable. DNA can inform decisions earlier, help prioritize investigations, and potentially support intervention before escalation occurs. This also has implications for prosecutors. In many gun possession and other public safety cases, complex mixtures are common. Having the ability to reevaluate those cases using advanced interpretation methods provides another avenue to strengthen investigations and protect the community. What we've learned from the experience is that it is not simply about doing more DNA testing. It is about finally listening to what the evidence is already telling us. The future of this model is to continue building a system that can scale, one that uses automated searching and ongoing monthly review to identify patterns earlier and more consistently. Ultimately, DNA should not just help us close cases. It should help change trajectories. DNA should not just solve crimes after the fact. It should help us identify patterns earlier, intervene sooner, and better protect the communities we serve.